It's a pleasure to have you guys here. I have worked with both of you as editors of the SAE Edge Research Reports for additive manufacturing. It's and Mike, your report is about to be published in August. Kevin, we already have 8 with you?
9.
9. All right, 9. Okay. All right. So you obviously both come from long careers in additive manufacturing and have seen a lot of changes in the last decades. From the materials perspective, what were or have been the biggest disruptors so far, and why? Mike, would you like to start?
Oh, sure. I would say one of the bigger disruptors from it isn't, I can't say a particular material that came on board on the polymer side of things. It really was the ability or capability to utilize commercial or commodity type material. The reason I feel that that's more of a disruptor was it kind of lowered the cost and the ability to get into the 3D printing. But also, I think more importantly, it created a familiarity to the people who use polymer for other things. So there's a lot of times where you're comfortable using a particular polymer. I'll just say like a particular nylon that you like, but you only have one nylon to choose from, and you're not sure what that nylon is or the differences of it, and so you're not comfortable with it. Like in the aerospace side, that we started off utilizing a lot of nylon 11, and that's what we were able to run in the laser sinter machines. But the automobile industry has a preference more towards nylon 6, albeit it's a small difference. It's in the nylon family. There are differences, and so that being able to use what you're familiar with opened up the world and really, I think, splashed and really grew the AM space. And I think that's why I would call that more of a disruptor.
Okay, very good. Kevin, what's your take?
So, we're currently using all existing alloy systems pretty much. On the titanium, it's Ti-64, Inconel, it's nickel-based, it's Inconel 625, 718. On the steel side, 316L. The biggest kind of, and I'll call it more of a surprise than a disruptor so far, has been aluminum alloys. On the aerospace side, aluminum is low cost to buy, it's easy to machine. And so when the incumbent process and material is relatively low cost, it makes it that much harder to close a business case. What aluminum has really done is that it's really benefited from the ability to design with additive. And so, even though the incumbent process and material may be relatively low cost, the savings, the benefits and improvement have justified the use to even switching from a relatively low cost material. Even though in many cases, right, the aluminum alloys that are most commonly used are quite a bit lower in strength than what people are using out of wrought material. So
interesting.
What you can achieve with good design for additive manufacturing practices.
Right. Wow. And from the perspective of applications, what do we see today in AM, in additive manufacturing, that we could barely imagine 10 years ago? Kevin, why don't you start?
So 10 years ago, and going back before that, it was all about, can we use this to make a more near net shaped part to reduce the cost? In aerospace terms, it's called reducing the buy to fly ratio. So, and it's for materials like titanium and nickel base that are expensive to buy, expensive to machine. And the shapes that were being made and the part configurations were just what you would get out of a machine part. The big change, and it really did start about 10 years ago, and people, kind of theoretically knew this, and on the polymer side, this had been demonstrated, 30 years ago, 20 years ago or so. But people started to realize with the flexibility of the process that you could design and you could make AM unique designs that you couldn't make another way to get, not only to get lower cost, but also to get better performance out of it. So, now we talk with a few exceptions, right? Probably 5% of the metals discussions are about reducing cost and buy to fly, and 95% are about either new capabilities or reducing cost with the new geometry, getting rid of assembly and weldments and things like that. So it's really moved much more from a one-to-one substitute all the way to whole new designs and analysis methods.
Right. So let's hold that thought. Let's see what Mike says, because there are more things to be discussed about the future and what you guys expect us to see then. So Mike, at this point, from your perspective, what are the applications that you couldn't imagine 10 years that would be here, but they are?
Yeah, I was going to say, I like the little disclaimer you added right there that I wasn't sure they'd be here 10 years ago. And I'm going to go with the build size. Early on, that was always sort of a limiting factor, at least in the aerospace industry, is having a build chamber that basically can fit in a hand. That's a very limiting factor as far as what you can do with it. So as the build size started growing, I think that is something I was hoping to get to a foot, 2 foot, 3 foot, and we did at that time, a little over more than 10 years ago. But then, just almost as Kevin said, almost 10 years ago, about 6-7 years, 2016 timeframe, they built one of the largest tools started coming out of Oak Ridge and some other areas, and then you saw the other companies come out of the things. And the enabler of that was getting it out of the box, getting it out of the controlled environments of like with the laser sintering or the fused deposition modeling type boxes, and getting it into the gantry bigger systems. I think that was the growth of the size that we can build today has sort of outpaced even what we were imagining 10 years ago.
Very cool. I think Alicia has some images to share with us, Alicia, right now, or no?
Sure. To point here, that was built a number of years ago as well, and it's just the size. It's hard. There's not a little ruler in there to scale it, but it's a very large part there. Just to show that all of a sudden we were building not little trinkets, but things that needed forklift holes in order to go off and lift it and to use it. That was just not something we were imagining. I'm going to go back to the very first part. One of the enablers of that also was the commodity plastics. Mm-hmm. Because you can afford to build that tool, and it would meet the business case of the tool because the plastics were, I'll say, penny, or I'll call it dollars on the pound. I don't think anything's pennies on the pound anymore, but at least dollars on the pound to enable it. But the size, I think, has just been tremendous. I think that's true on the metal side as well.
How about these? Same thing.
These are little. These are
I get that.
Representing the little ones, but important nonetheless. Well, we can stop the pictures here for a moment.
Yeah. Okay. Yeah. Are these enough? Very good. Thank you so much. So, talking about materials in general, now we see more materials coming through and being added to the mix: metals, polymers, or composites. Which and when? Can you tell us more, Mike?
Putting things into polymers is really, it's nothing new. Polymers is all about a little mixture of things. Obviously, just in the name itself, it's a mixture of things coming together. So even from the very beginning, UV inhibitors or things that helped the plastic survive in the applications have always been added to things. Flame retardant. We started adding little milled carbon to help improve stiffness of the plastics. But where I see it going, at least on the polymer side, is getting into the longer fiber, carbon fiber or longer glass type fibers, to start eventually getting into truly structural composite materials. So that's an exciting thing that we'll maybe talk about a little bit later, but getting into structural composites printed that don't require the tools. That's an exciting branch, and I think getting into that area is the new mix that's coming on board, but not so much just the little additives.
Right. Yeah. And Kevin, you had mentioned aluminum. Anything else, or would you like to talk more about the new materials that are coming into the mix?
Yeah. when you were first asking this question, I was thinking of answering, the whole thing. And I just, a couple of years ago, I was at a meeting and a composites person said, who worked with laminates, was like, we're the original additive manufacturing. That's, we've been doing it for 60 years. But, the polymers, started early in applications. They were, the ease of processing and such, got them implemented in the ability to make complexity. Metals is really, in terms of applications and properties, people are looking for the next thing. And so that's why metals has seen such growth in the last, I'll say, 6 or 7 years and in terms of interest. There's, going back to composites and metals will continue to do that. There's lots of applications. I'll talk about that a little bit later. But, the ability, I think, for the kind of the material of the future is, when you can make composite parts and use additive technology to get better strength in the Z direction. Typically your composite laminates have almost no strength in between the plies. But if you come up with better ways of building parts in 3D versus 2D, that additive gives you, you'll be able to get that.
So if I were to ask you guys, in terms of the bleeding edge of new materials, would you bet on any for the next 5 to 10 years? Anything that is just popping up on the marketplace or labs?
So you're starting to see people developing alloys for AM in the first place. The first of these has been out for almost a decade now, was Scalmalloy, that was developed by AppWorks, right? It took advantage of the processing, the rapid solidification you get in AM to make a very strong aluminum with pretty simple post-processing. And it's been, it's been quite successful. It's grown, and I think they're even coming out with a newer version of it now. But that's one. There's other ones that are going to come out in the future as well. But that's going to sort of get us to the next level of performance. You're seeing this. It's been starting in kind of the university level for five years or so, and those are still probably 10 years away from implementation. That's in typical industry. That's how long it takes to implement something.
Wow.
And in industries that are really property dependent, and when you're making a real step change, you have to really understand the material.
Yeah.
But those designed for AM. I just was recently at Rapid, and an ATI introduced a titanium alloy that's easier to print and just as strong as 6.4. So it's a good one. And they also have a nickel-based alloy that has really good creep resistance that takes advantage of the AM. So we're starting to see people take advantage of the processing to get better material properties than you can by taking an existing alloy. Well, figure out let's make powder out of it and then print it.
Mm-hmm. Interesting. Mike, what do you think? Do you agree with this or you want to add to it?
Well, I definitely agree with what Kevin is saying on the metallic side. On the polymer side, I'm not seeing new polymers invented for additive, similar like on what Kevin was referring to on the metal side. But we are seeing new things added, to your prior question, mixed into the polymer to enhance or change the properties of the base resins. And you're starting to see it maybe that they're tailoring it to specific applications. They're saying, we can change it by single percentages. Instead of buying a particular plastic with 30% something in it, now you can get it with 27% or 16%. What do you need? We'll make it for you. So more of this compounding that's coming up of creations, specific coloring that they want to add to it, or whatever kind of property that they want. You're seeing these customized polymers and blends coming into the market. So it's not a particular plastic that I'm seeing invented, but the mixing of the plastics and the ability to go out and print those is opening up the application spaces.
Right. So what I'm hearing is new alloys on the metal side, different mixes on the polymer side.
Which is essentially an alloy. Yes, in a way it is. It's sort of mixing different polymers together to get kind of a different blend and an alloy of particular.
Right. Right.
Polymer.
Yes. Very interesting. So I have another question here that I've been wanting to ask you guys. With the industry gaining more and more momentum, do you also see other material systems becoming important in AM besides the ones that you have described? If they are the ones, then we can move on to the next conversation. So is there anything that is even more than bleeding edge? Or you would rather say, Monica, let's not go there because it's too new?
No, let's go there. I like going there.
Okay.
The new phase. Again, I think for me, it's again not a particular material that hasn't been broached or not been used yet. It's going to be the integration or hybrid of multiple materials being grown in a single build. We're getting out of the box now, so we're not going to be limited by certain environmentals potentially, or maybe do localized environmentals, but we're going to put different materials together. So it's going to be all about the interface or the potential gradation of the material blending together to create a singular phone, or print the phone, or I don't know how many times I heard, go print me a wing, where it has all the different components already printed into it. So I believe in the future, and again, I don't think it's that far out anymore, it's going to be the blend or the hybrid printing, which is going to be fun and exciting for M&P.
Definitely. Kevin, what do you think?
So in terms of material systems, ceramics has been sort of around for the last 15 years. I think I saw the first ceramic printer about then. And ceramics are never going to, grow to the size of polymers and metals, because some intrinsic aspects of their properties. But, the ceramics people will be able to start figuring out how to design with AM. This is going to be more binder jet. I think they're also waiting on binder jet systems to become more widely available. But you'll start to see that in areas that are, for high temperature applications.
Right. Yeah. No, cool. Mm-hmm. So looking into the mobility sectors, aerospace and automotive often come up as adopters of AM. But when we look at the commercial vehicles, it seems that and please do correct us if I'm wrong, correct me if I'm wrong, but we don't hear as much of the commercial vehicles integrating AM into their builds, into their product designs. Is that true, or they just don't talk about it, or I don't know about it? But what is your opinion on that?
So aerospace was first because it's used to putting new materials in and new processes in all the time. Mm-hmm. And the initial processes were slow and costly, and so aerospace was willing to pay that premium for that cost. And also aerospace being lower production rate, it also more aligns with additive, kind of intrinsic feature, right? Single part production. Automotive, personal vehicles and light trucks, it's still mainly talking about the future. Everybody's dream is, well, if I could get 1 pound on every car made, this would be wonderful, right? And implementation is happening in going to that. Commercial vehicles probably have a higher percentage of their weight or percentage of their parts made with AM than cars. In fact, one of my first EDGE reports I wrote, one of the collaborators was Jen Coyne, who is at Wabtec. She's now with us. Mm-hmm. And it was about, locomotives, putting it in there. Commercial vehicles are sort of in between aerospace. They're not willing to pay as much of a premium, but they have the low production rates and the specialization. And, I will say, in some ways, I think the commercial vehicles consider it more of a discriminator and more of a competitive advantage, and they don't talk about it as much intentionally. but I know from talking to service bureaus and people that contract manufacturers are like, yeah, we're doing a lot of work for this company and that company and this company, and they're not making, they don't make cars, they make, as we say, yellow products.
Yes. Very true. Mike, what's your take on this one?
So I agree. I don't want to say, I think you're correct in that it's not talked about as much, but I don't agree that it's not there. I'm going along with Kevin on this, that it is, I would say additive is being utilized across every commercial vehicle sector. The trains, the light and heavy trucks, construction equipment, it's all being utilized. It's just not as, I don't want to say, it's not the hot and sexy topic that they want to write about in some of the articles of aerospace or to a space vehicle or something like that. But they're all utilizing it somehow. It might not be on drive-away parts or rail parts, whatever, but it's going to be utilized in the production processes. I think additive is all over the place. You see a lot of them being utilized. Ellen Lee was one of the, at Ford Motor Company, was one of the editors on, or contributors, I should say, on the Edge report coming out soon on the composite side. Yeah. Ford's heavy into additive manufacturing. They have been for a long time. So the automotive side has the sexy part of the quantity that they're pushing out and the new vehicles and how quickly they have to turn out new models. But the more other vehicles are not just talked about as much.
Right. Yeah. And, these are micro-cultures of each part of the mobility sectors, right? Or the industry. They behave differently. But that's why I wanted to really know what your take is, because you're out there, talking about this. I think we have some questions that we would like to break for. Yeah. Just 1 second. Alicia is going to be Alicia, and we'll be talking to you guys.
Okay. All right. Yes, we have one question in the chat. It has multiple questions, so I'm just going to read one for now. I want to apologize in advance if I mispronounce the name, but these questions come from Saruli, and they are asking, how do you foresee the future of AM in the next coming 10 years ahead?
Okay. Each one. What's your take, Kevin? You're writing about this right now.
So the big things coming up in 10 years is going to be bigger machines and really getting the cost down. When people say, what's the biggest barrier to AM, wider implementation, I say it's always cost. It's really hard, especially in high volume industries. It's really hard beating a stamping press with sheet metal. It's hard to beat the efficiency of sheet metal. Sheet metal, probably 90% of what an automotive company buys winds up in a car or a truck somewhere, right? And so it's hard to beat that efficiency. So you have to do it by by either weight savings, which is driving a lot of it, or by getting rid of assembly savings. But you really have to, get the cost down. Automotive is like 3 orders of magnitude more cost sensitive than aerospace. And we're starting to see that. About a year ago, a company announced that they had orders for 100,000 automotive parts. So that's not Lamborghini, that's not Porsche, right? That's probably someone Audi or BMW. You're getting into these higher quantities, and as cost sensitive as automotive is, it always has to be saving them something. If it's a 100,000 vehicle market, so the big changes are going to be cost. That's going to really expand the usage with the faster machines. The other thing is as more confidence is gained. This is going to be more so on the aerospace side. As more confidence is gained, you'll see it going into more and more critical parts.
Right.
More common. There's already some critical parts out there, especially on the rocket side. There's also, I will call it, business critical parts. I'll talk about that a bit later, that are implemented now. But 10 years from now, every airframe and engine manufacturer will probably have one critical part that's AM, where
at least.
Yeah, the part breaks, the system fails spectacularly. So
yeah. Definitely. Mike, what's your opinion on this?
Complete world domination. Additive manufacturing is going to take over every manufacturing process and only be it. And obviously, I'm joking because that's where the hype comes from in that. But I do see it as, again, to Kevin's point, it's just going to become more and more commonplace. It's just going to become another tool in the manufacturing toolbox as costs come down, as comfort level goes up. That's what it's going to be. It's just going to be another thing to get things made. And it's going to maybe be more of it as they bring the cost down and those cost curves move over to the right-hand side, and that justification is allowed to happen. So it's going to be something, another tool, another screwdriver, another hammer.
Right. It's another round of innovation using that technology. Do we have any more questions that you would like to post?
Yeah, and actually there was a follow-up to that question. It was, what about the sustainability and carbon footprint of this process?
Okay, Mike, let's start with you.
That's been an interesting question for me even for a couple of decades now. I remember a project, I think they called it the Atkins project at the time, related back to the Atkins diet time frame of how it really took out the fat of manufacturing processes, and therefore thus being more sustainable. It came out of the Europe side over in England, UK. And the reality was it does to an extent, but when you take in the whole process, which is from the creating the feedstock to the final part that gets delivered, there wasn't near as much savings as they thought. To get to a monomer to a final product, it's pretty consistent of what you're going to have to do, the energies that you have to put into it. They can say, hey, we can print it right on the spot. Therefore, we're saving money, not having to transport the part. But at the same time, you're still transporting the feedstock. You still have energy into the feedstock. And so there wasn't that much of a savings on that side. But to Kevin's point earlier about buy and fly, if you're not having to buy as much material at the get-go, there's a savings there, an obvious savings.
Right. Thank you. Kevin, additional thoughts on this?
Are you selecting these questions so I can discuss prior edge reports? So the one came out, I co-wrote with Ellie Foos, now with Trump.
Yeah, exactly. Yeah.
And we analyze these, and since everybody sort of, was kind of holding things close to the rest, we did some analyses, and the biggest savings in terms of energy and in terms of that is going to be if you can make a transportation system more efficient. So, we looked at just taking a part out of an engine, a theoretical part out of a theoretical engine, and reducing the weight and improving the efficiency of the engine. The savings over the lifespan, I think something like 98% of the CO2 emissions reductions over the lifespan of the system came from it being more efficient, and 2% came from it taking less feedstock and more efficient operations to turn it into a part. And so really the real focus, has to be is on getting the performance, which is really where DFAM and all this has been going to with these unique parts and structures you can make. That said, how you do I know someone just recently came up with something that said, there's really no benefit there. I don't quite agree with how they did their accounting, but you have to look at it, like the Atkins project, you have to look at it holistically, which is, where are these different things going? How much is getting recycled back in? And there, that ability to do those calculations are there. But, overall, it's, unless you do things poorly, right, you do have a savings that comes both in manufacture and in service. Or the thing is, right, you're not being forced to use AM, so you're only going to implement it for those reasons if you're actually getting a savings. So.
Correct. Yes, thank you. I will continue with the interview. Or do you have anything?
One more.
Yeah.
Just have one more.
Yeah, let's go ahead and do one more from Ethan. We have, do you see any change happening in terms of metals versus composites in part applications?
Thank you, Ethan.
Well, I can take a quick stab at that. Change happening in the part application. So how metal, or I'm assuming you're sort of saying between a metal business case and a composite business case, because that's ultimately what's going to decide it. The business case of it or the performance of that part, to choose between them. I would potentially 3D printing, if you can truly get to a composite that's comparable performance-wise to a metal, and you're able to do it without the tooling costs and the processing, potentially you have a chance to have more composites available. But it's all going to come down to the analysis, as Kevin talked about several times, on the costing part of it and the business case to go forward. And the application itself, whether metal is better suited for the application versus the composites, whether it's environmental, thermal, or chemical type things going on. So there's a whole lot of it depends in there, but I don't really see the only way composites will start doing more on the metal side will be better performance and better costs. Lower cost, I should say.
Kevin, would you agree?
Yeah, I don't really have much more to add. It's going to be very application specific.
Yeah, no, totally. Okay, so you both are editors and have been the editor research reports. And for that process, in developing that kind of content, you took the pulse of the industry. So the question is, today, what are the biggest concerns that you hear about? And what are the biggest wins that the industry considers to be landmarks to take the AM to the next level? Kevin?
So the biggest concern is going to be cost. Whole ranges of industries have shown that additive manufacturing can meet the performance applications. It's really about cost. In some ways, it's a little bit also about meeting rate, but rate and cost are really, interchangeable, right? You can always buy more machines, install more machines, and, have, acres and acres of printers to do that. So it's really about cost. The biggest win, I kind of turn this around to, what on the metal side, what do I consider the most impressive AM implementation to date? And I'll have to say it's GE's using thialuminide for those turbine blades. People have been working thialuminide since I was a college student. And the challenges with processing it, the brittleness was always a barrier. GE found a way that by combining additive manufacturing and that system, they're able to get a breakthrough in performance. They're able to get the performance of a nickel-based alloy at less than the density of a titanium alloy. And not only, is thialuminide a tricky material to work with, a tricky material to actually just to make, but not only is it impressive, the technical accomplishment, but they had to have confidence that they were going to succeed. And you can't redesign the engine and say, oh, we're suddenly going to go with nickel turbine blades. It's just the engineering is too intricate for that. So, so not only was that a critical performance application, but that was a critical business decision, right? They were betting the future of their engine business on being successful. And that's what makes it so impressive.
Right. Yeah. Interesting. Mm-hmm. I hear you. So, Mike, what would you add to that?
So I would say the biggest concern and the biggest win in a single answer would be consistency of it. And it also comes into the EDGE report coming out on the long fiber, the continuous fiber printing is, can you make the millionth part or thousandth part look like the first part? It's going to be in the consistency of that's from the very beginning of 3D printing was, sure, we want to do this, but I don't know if you're going to be consistent enough to get onto this vehicle or to this production. Why do I want to take the risk of it without knowing? So again, the concern always has been, besides the cost and what rate you're going to be using, has been the consistency. And so that's how important it is with things, people like SAE and others coming into and writing these specifications, both on the material side and the process side, so that you can have a consistent product going into your production line. So you're not putting risk into that production line or risk into the use of the application. So the big wins have been when somebody's been really consistent, they're able to get that part onto a vehicle, even some very important parts onto very important vehicles, because they've shown consistency of that application. So I think that is, again, one of the still concerns every time we have a new application, or I'm sorry, a new change of the technology, like, again, continuous fiber into the printing process, but it also becomes the biggest win of the process as well, the biggest win of that.
And so just to expand a little bit on what you're just saying in terms of consistency, that would also impact, I imagine, the predictability of quality, right?
Yes.
And the maintainability of the part.
Yes, yes, and yes, yes, and every other feature of the part that you're trying to put in there. Yes, it has to be quality. The quality has to be in the DNA of the part itself, and that you know that it's in there, and that you're willing to know that if I do it again next week, that same quality is there. If I do it next year with the same material, same process, I'm going to get the same quality out of that part.
Yeah, totally. So now I'm going to ask you guys a little bit of more personal questions, nothing too personal, but just wanted to know, what was the first thing you ever created using AM? And what are you the most proud of working on?
Well, I can say I remember kind of dating myself, but coming out of school in 1987 and getting into this small group that pulled out they brought a little machine in from California with the 3D Systems logo on it. I had no idea what it was, but printed out it was a tiny little build chamber, printed out these little plastic configurations of vehicles. That was one of the first things, and at that time, not knowing the industry that would come out of it, how to rise out of there. But I would say I've had the opportunity we've printed a lot of different parts, a lot of different things for a lot of different programs and other customers as well. But I'd say the thing, I'm going to turn it around a little bit. The thing I'm most proud of is really the interaction of all the people that I've gotten to dealt with over the decades. It's just a tremendous quality of persons that have been working in the additive industry. Some have become lifelong friends and acquaintances, not just within the company I was working with, but also the companies that I worked with as well, outside of Boeing. So they all have a passion for additive. They all want to make it great and do things, albeit some of them are, I think, a little misguided. That's my opinion on that, but they all want it. And so it's just been a tremendous amount of people that I've gotten to work with, and a great quality people.
Yes, awesome. Yeah, that's great. Kevin, how about you?
So the first parts were the process, but actually, the first parts we actually implemented, 20 years ago, were actually about 6 years into working the technology. It seemed like for 4 years, the main role of the technology was to get the incumbents to lower their prices by coming up with an alternative. But so that was really the first thing, and of course, being the first in the industry is something to be proud of. Also, we recently wrapped up a program for the Army and helped them with down select and helped them build a supply chain. And very proud of the fact that we were able to deliver a tremendous amount of value to them. We weren't planning on getting AMS specifications out. We weren't planning on getting any hardware flying on Army helicopters, and we actually achieved both of those. And we did it almost entirely without ever actually seeing anyone, because there wasn't a lot of traveling going on in 2020 and 2021.
Right. Yes. Thank you. Thank you so much. Do we have any more questions? We do have a couple of questions. Alicia, please.
Yes, we have another question. They're asking, is process consistency equal to process repeatability?
Yes.
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 Following the process and being able to repeat it. Yes, that is.
Absolutely. And then so we have a question from Iris. How is recycling of parts going?
So on the metal side, there hasn't been much of opportunity because most of the implementations are rarely recent, and the equipment's still in service. Internally within the process, the excess powders, the wires, they're all really using the existing recycling chains. Engineered materials. I think I saw a while back, and this is copper, which is a relatively low cost material, but something like 90% of all copper gets recycled at end of life.
Mm-hmm.
And in titanium alloys and nickel-based alloys, you see the same, that they're the recycling rates at the end of life are very high because of the value intrinsic in those materials. And internally, you're seeing the same thing, that they're getting recycled. So,
and obviously it's going to go much better on the metallic side than it's going to be on the polymer side. Polymers, every time you apply them, you do a degradation to the material. So you're not going to see it really cycle into a part coming off the aircraft, get recycled to another part on the airplane. I don't believe that's going to be happening. But you can recycle it into a park bench or an Adirondack chair that you can put out on your deck, just because the requirements are going to be so much lower. However, I think as time goes on, as I was talking about earlier, as you start mixing in different things to it, and all of a sudden instead of just having one kind of a nylon, now you have 1,000 different kinds of nylons. It's going to be a bit harder to do some of that recycling because you don't always know what they're mixing into those polymers. So there's pros and cons of each of what we're doing. So recyclability, as Kevin Ian said, they're utilizing the existing recycling chains currently. When polymers go bad or when you're done with them, they do put them into, stamp them and try and recycle as much as they can.
Thank you both. Thank you.
Do you have anything else?
We have one more. Sarah is interested in knowing, do you see integrating a sacrificial layer or barrier or coatings with metals and polymer in the near future?
Thank you, Sarah.
I'm not sure what that's asking, so I'm going to give it over to Kevin.
So, that's what I would call hybrid manufacturing. The kind of the first stage of that, people are already doing, right? They may be printing a part, and then at the very end, add a hard facing to it. It might not be in the same printer. They'll oftentimes, because the cost of the printers and to operate them, right, you're going to go and you're going to take that out and put it into a lower cost process. But people are already doing that with, I'll say, mainly metals and ceramics combinations and wear faces. They're going to see some in the future of, people talk about, well, I can use a temperature resistant material here and I can use a stronger material here and grade the composition. And that, at some point that'll happen. There's lots and lots of pitfalls to that, and it's very difficult to do. And there's always going to be limitations on what material systems you can have at one part of the structure and one at the other to avoid, doing things like intermetallics and other things.
So I'm going to add to that now that I've heard Kevin's answer, because I misheard the question. I was thinking that during you build, you want to have a sacrificial layer, but you're talking about as you're building, integrating, as you're saying, hybrid into it. I think that's going to be happening in the much nearer future than we're even thinking now. But just because you're seeing it, one, out of the box, two, you're seeing robotic type things coming along, robotic robotic systems coming up where they're depositing material, they're machining the material as they need to, or machining it down, easily could come back through and spray on coatings in the same chamber as well. Because so I think that's going to be happening, if it's not already happening currently in some internal places that haven't been advertising it.
Thank you. Kevin, any final words?
No, not really. Just we're still early on in this industry, and there's there's going to be lots happening in the next decade. So it'll.
Mike, how about you? Any last words?
Well, the last words, I think there's times where I feel like the additive industry kind of stagnates a little bit. It just seems like it's not moving anywhere, but it is. It is slowly and everywhere. It's just growing and growing and growing. You just watch the curves of the use cases. It continues to grow, maybe not at the speed that I hope it'll grow, because as I'm getting older, I'd like to see certain things happen in my lifetime, but I might not. But it is growing. But also, I'd like to again thank you, Monica, for this opportunity to be here today.
Absolutely. So thank you all for being here with us today. Special thanks to you, Kevin and Mike, for a fantastic session on additive manufacturing and material systems, on your experience. And we will post a recorded video on the SAE International video YouTube channel and share the resources.